Hey there, everyone. How's it going? I guess before I get started, I'll say that it's kind of a small session. So if anyone has any questions during this, feel free just to shout them out. I actually prefer to be interrupted during my talks. So if anything doesn't quite make sense or you'd like to share a comment, please feel free to weigh in. But yeah, thanks so much for the introduction. I'm Mike Merrill. I'm a postdoc at Stanford, and I'm going to be talking a little bit about our project, Terminal Bench, which is a hard benchmark for language models as agents in realistic terminal environments. And so I'm going to kind of break this talk down into two parts. In the first, I'll talk a little bit about why I work on evaluation and why I think this is a very exciting time to do that. And then in the second part, I'll talk about Terminal Bench, which is our project and a frontier benchmark for agents, and what's next for that project and what we're planning on working on. So why should we work on evals right now? I think in part because this is really just a very exciting time for them. If you look back into ancient history of 4 years ago, language model evaluations were very much focused on what does a language model know. So most popular benchmarks at the time directly compared inputs and outputs in multiple choice style evaluations. A great example of this is MMLU, which was one of the frontier benchmarks for language models for a number of years. And these evaluations had very well-defined criteria. It was like taking a test in school. So you had a multiple choice question, you had one question that was right, and they were very easy to score and nicely specified. And these were all single turn evaluations. So only looking at inputs and outputs of language models in these static environments. You can contrast that to what we have today, which is much more of an emphasis on what can AI actually do. What are the valuable actions that it can take in the economy and work that can be performed by a language model? And I think one of the best examples of this is the benchmark SWE-bench, which I'm sure many of you have heard of, which focuses on whether or not language models and agents can resolve GitHub issues. Given a description of an issue and a set of unit tests, can the agent get all of those tests to pass inside the environment? And this is very different in contrast with traditional language model evals. Instead of looking at just inputs and outputs, we're comparing actions. We have language models operating in the interactive multi-turn environment where it can use tools, it can scroll through the repo, it can maybe query the web for outside information to help it solve its problems. And we are evaluating language models in these much more dynamic, interesting environments than we were just a few years ago. And I think this is particularly exciting when you consider that empirical research shows that the time horizon that language models and agents can operate on is getting longer and longer and longer. So this is a great plot for meter, and on the x-axis here we have the release date of a language model, and on the y-axis we have the duration of the tasks that these agents are able to accomplish. And so we see, going back as little as 2 years ago, we have models like GPT-4 that struggle to accomplish tasks that take on the order of a few minutes and are only able to do things like find facts on the internet. And then as you push forward just 2 years, you get into this regime over here on the right where we have GPT-5 and Grok 4 that are able to autonomously perform tasks that take hours. And these are things like exploiting the buffer overflow or scraping records from a website by bypassing its bot protection. And we're starting to see agents and language models be able to perform the types of real tasks that humans do in the economy, which is very exciting. And so if we're in this regime, this means that in order to understand frontier language model capabilities, we also need increasingly complex long horizon benchmarks. The tasks that took just a few minutes to specify and to verify are saturated for language models, and we need more tasks that exist on this frontier, like exploiting a buffer overflow, in order to measure the capabilities of these models. So it's a very exciting time to build benchmarks, because we're changing both the way that we evaluate models by going from these static benchmarks like MMLU to SWE agent, and we're also in serious need of benchmarks that allow us to understand the capabilities of frontier language models. And so this is where Terminal Bench comes in. And I guess I'll take you a little bit back to my thinking and the thinking of my colleagues a few months ago to give a little bit of motivation for why we thought that understanding how well language models could perform tasks in the terminal would be an interesting thing to work on. So the terminal is a great interface for language models and computers. It's text-based, meaning that it's the modality that still works the best with language models. It doesn't rely on GUIs or computer vision in order to interpret what a computer is doing. It can just jack directly into the terminal and accomplish real work. It's incredibly powerful. You know, the terminal is the testing ground of all these stories that you hear about legendary engineers who never take their fingers off the keyboard and do everything in Vim and Emacs. And so we know that the terminal can be used to do almost any task on a computer with just one tool. And the terminal is highly valuable. It's used by experts in countless domains to do real tasks that are inherently valuable. Not just systems administrators and software engineers, but also scientists and AI researchers. And so being able to do real work in a terminal-based environment could translate to these frontier tasks that we care about when we're evaluating language model performance. And I think maybe one of the best ways to explain why this is so interesting is to look at a motivating example. So we all know that it's a great tool, and we see this even with our best engineers. So if you've ever tried to configure an AWS instance by using the GUI, you know that it's a pretty cumbersome process. You're clicking through dozens of menus. You're trying to get your right storage equipped to your instance. You're trying to configure your security, your keys. You're trying to figure out which instance you want to provision. And it's a process that's like not exactly intuitive and could take quite a bit of time, even for someone who's relatively experienced using these tools. In comparison, there's just a single CLI tool that can be called to accomplish this same action. And if we knew what exactly this tool was and were able to remember it off the top of our heads, then we'd be able to accomplish things much quicker than we would if we relied on navigating using a GUI. And this is because the terminal is such a powerful environment that allows us to shortcut these limitations of a GUI to get real work done. So what if our AI agents worked like our best engineers? To some extent, they already do. Virtually every frontier lab has launched some form of a terminal agent to help people accomplish work inside the terminal. You've got your Claude Code from Anthropic, your Codex CLI from OpenAI. There's a Gemini version of this now. Cursor's released a terminal-based agent. The SWE bench people have released their own minimal terminal-based agent. And we're really starting to see this growth in tools that are specifically focused on building from inside the terminal. But it's also not just these dedicated CLI agents that interact with computers using shell commands. Even agents that I'm sure you've heard of or used before, like Cursor or Manus, all use CLI tools to do things like edit files or operate web apps. So like the terminal shell is a very fruitful area for agents to control computers. And here's a tweet from Guillermo Rauch from just a few months ago where he says, it's 2025, some of the most impactful products in the world are CLIs. Coding agents love running CLIs. ChatGPT solves problems by writing scripts in virtual computers that invoke CLIs. This is just to underscore my point that this is a very powerful environment that I think is worth studying. But how do we know that terminal agents are actually ready for production environments? What's to stop a language model from issuing a command like this? It's clearly very important that we understand the capabilities and the limitations of agents inside these environments. And so that's why we built Terminal Bench, which is our benchmark and which is what I'll focus on for most of the rest of the talk. So what exactly is Terminal Bench? And I should say that at the end of the week, we're releasing Terminal Bench 2, which I'm very excited about, and maybe I'll get into in a minute. But Terminal Bench 0.1.1 is 80 tasks that were written by humans who are members of our open source community. These are, for the most part, PhD level contributors who are submitting tasks that are based off of real things that they've had to do in the course of their careers. Each task comes with a verified ground truth solution, so we know that a task is possible. It comes with a set of test cases to verify that the agent has done its job. And each task comes with a unique Dockerized environment that we serve and use as a test bed for understanding the capabilities of these agents. Some examples of these tasks include compiling exotic code from source, data processing pipelines, real scientific computing workflows from biology and physics. And the point here is that these are like all things that people would actually want to do. There's no toy examples. Everything that we've included is something that a real person has struggled with at some point and that we know that language models struggle to do now. Let me break down for you a little bit more concretely what exactly is in each of these terminal bench tasks. So as I mentioned, we have a task architecture, which is a very simple specification. It's just a Docker container and a description of the environment, which is a set of instructions, in this case, telling the agent to re-implement a COBOL program in Python. And each task comes with a solution, again, so that we know that the task is possible, and a set of tests, which when executed are going to tell us whether or not the agent has accomplished its goal. So the workflow here is that the Docker container or other containerized environment gets instantiated according to the specification. The agent gets installed or activated inside that container, and then it's given the instructions to go and solve its problem. I should say, like, just sort of off the cuff, there's one thing that I think we really got wrong with Terminal Bench, and that is calling it Terminal Bench. I think probably more accurately, we should have called it something like Container Bench, because while we were initially interested in this paradigm of how agents can interact through terminals, that's far from the only way that agents do in practice interact with our environment. So we support other agents like OpenHands and Aider, and we've been used to evaluate cursors, agents, and all of these come with their own tools and don't strictly interact through the command line. But nonetheless, that's the name that we picked, and that's the one that we've stuck with so far. But the point I want to make here is that we support this evaluation of arbitrary agents where we can just install them into the containers and understand how well they work, which I think in an increasingly agentic world it's more and more important to actually test how well these systems and workflows work. So that's what a terminal bench task is. That's how it operates. We built it to be hard. When we released it, the state of the art was only about 50%, which tells us that there's still plenty of room for agents to improve as they continue to develop. We built it realistic, as I mentioned, so every task is based off of something that someone would actually do. And we built it to be live. So the benchmark is versioned, but ever expanding and changing as new model capabilities are unlocked, which, as I mentioned, has led us to release Terminal Bench 2 later this week. We were really happy with how the benchmark was received. 3 days after it was released, it made it onto the Claude 4 model card and was one of 2 benchmarks mentioned by Dario during the model release. And now we have 1,000 stars on GitHub and over 100 contributors to the project on GitHub, in addition to 1,000 members of our Discord channel who are helping us build new environments and work on our software for running and evaluating agents in these environments. I think also something that was really exciting to me when we were on the Claude 4 model card is that this was the lowest score that they reported on any of the benchmarks. So these other benchmarks that had come before, benchmarks like Tau Bench and Sui Bench, had much higher scores, implying that there was a great deal of room to improve and that we were pretty far from being a saturated benchmark. This is a ranking of models and agents on Terminal Bench 1.5, which I don't think we will ever actually release, but was a stepping stone on the way to Terminal Bench 2. I think something that's particularly interesting here is that we see that there are combinations where a provider's agent works best with their model. So for example, like GPT-5 works best with Codex CLI. All of these scores here are the highest performing agent for each model. But there are also some surprises here. Like we did evaluate Claude Code, and that didn't end up being the best agent for any model. And actually, Claude Opus 4.1 performed best with open hands. Something I also like a lot about this plot is that we have this nice stratification of agents. So we see that as agent and model performance increases, we sort of like linearly see the score of these agents and models increase. I'll share a couple of things that we noticed while we were running these experiments. So the first is that GPT-5 loves to try to use Nano to edit files, even though it's not very good at it, which is a bit like me. And it's also quite bad at writing JSONs, and it'll frequently trip itself up by trying to generate JSONs and then fail to actually produce correct syntax. Another one is that this agent Goose will often tell you what to do rather than doing it itself, much like a senior software engineer. And there's a few other things I guess I'll share. Like we found that Claude 4.1 Opus had this, was particularly likely to do anything it could to try to solve the problems, even if that meant hallucinating and just guessing at what it thought the right solution would be. So if we gave it some tool to use and it wasn't able to use the tool for one reason or another, it would just make up whatever it thinks the likely result would be. And you see serious differences in the ways that these models perform. There's some real stratification across behaviors. I think this is a particularly good example. So this is one where GPT-5 is trying to build the Linux kernel from source, and it's gotten stuck inside of Nano, and it keeps on trying to get out by issuing commands, which don't work. And then it gets kind of frustrated and just starts spamming Control-X to try to get out. And then I think it'll probably even do that again. Yeah. It doesn't know what's good for it. But yeah, I think something that is worth pointing out here is that there are these predictable themes of agent and model failure where we're able to classify these, and hopefully model makers and developers can use these insights to change the behavior of these agents. So what's actually working? Like what leads to better performance on Terminal Bench? The leaderboard's been up for, I guess, about 5 months now, and we've had dozens of submissions. One thing that we've found makes a big difference in model performance is this phenomenon called model alloys, in which agent makers will dispatch their API calls to an ensemble of different models. So like one really sort of silly thing that actually works quite well is you can basically flip a coin every time you're planning on making a call to an LLM, and you can copy that entire context over between your conversations between these different providers and switch which model sends its input during each turn. And you can kind of think of this as like an ensembling technique, but it seems to lead to about a 5 or 6% performance increase on Terminal Bench. The other thing that's making a huge difference is just better models coming out. Like I think Sonnet 4.5 is the highest performing model right now across a variety of different agents. And like we are starting to see the state of the art creep up to 60, 65%. And so this was just part of our motivation for getting a second version of the benchmark out as quickly as possible. And the third thing we found is that making custom modifications to scaffolds to help the agent get unstuck can lead to a 5 to 10% increase in performance. So an example of this is that in our own agent, we've given it the option to cancel a command early if it thinks that it's been running too long. And this prevents the agent from timing out by just issuing the wrong command and then sitting there infinitely waiting for it to finish. And so just like dumb little optimizations like this can actually translate to pretty significant improvements in model performance. So I just shared about Terminal Bench, which is our project, and now I want to talk a little bit about something new that we've been working on as well. So what did we learn from building Terminal Bench? One thing was that people were building in unexpected ways with our harness. We found people using Terminal Bench for prompt optimization, as unit testing for their agents to check for regressions before they push to prod. People were hacking the Terminal Bench harness to allow them to do RL rollouts on top of our environments and ones that they create for themselves. We had all of these benchmark makers coming to us asking if they could use our harness to develop their own benchmark. And so we really wanted to support this in some way, all of these different use cases. The second thing that we learned was that there's a huge demand for training agents with RL environments. This is a real cottage industry that has popped up over the last few months, is going out and building RL environments and selling those to labs or other model makers to train their agents. And we wanted to support this paradigm of bringing your own arbitrary environment and then just training an agent on top of it. And the third thing that we learned was that it's very difficult to parallelize the creation and launching and maintenance of these environments. When we built Terminal Bench, we were running everything on Docker locally, and this scales to about 6 concurrent environments. But in order to run much larger scale experiments, we knew that we needed to scale up into hundreds or thousands of concurrent environments. And so in order to do this, we built Harbor by Terminal Bench, which is our one-stop shop for building the best agent with whatever framework you're interested in. And the purpose of Harbor was to address some of these unanticipated pain points that we found while building Terminal Bench. What Harbor brings is the option to evaluate any agent on any benchmark. We've abstracted away much of our code for running Terminal Bench in particular, and have made it easy to port benchmarks like TauBench or SweBench or any of the other frontier agentic benchmarks, and probably any agentic benchmark to come out for the next few years. We also now are working on integration with SkyRL, which I think Philip and Tyler are going to talk about in a later session later today, or at least SkyRL in general. And we've made it possible to parallelize generation and evaluation, not just on Docker locally, but with Kubernetes, Docker, any of these neocloud providers like E2B, Runloop, Daytona, Modal. These can all be used as the hosting platform for environments that integrate directly into our harness now. And I think something on top of this that I may have mentioned already is that we support any arbitrary containerized environment. So rather than just focusing on Terminal Bench tasks, you could imagine someone using this for running one of these Salesforce or Slack clones that are being sold as environments across the city right now. So we're really excited about this. It's going to be launched later this week. And the highline takeaway that I would have here is that this is everything that we learned from months of trying to evaluate agents, every problem solved, packaged up, and ready for other people to use. So we are hoping that this helps take a step forward in agent evaluation and training, and we'll have more news on that later. So if you're interested, these are 2 QR codes that go to both the Terminal Bench website and also to more information about Harbor. And please feel free to join our Discord and ask any questions or follow up with me afterwards. I also just want to give a quick shout out to the team. As I mentioned, this is an open source project. It wouldn't have been possible without people from dozens of different institutions across the world coming together to help us build these tasks, give us feedback on the software, and do all of the nasty work of plumbing agents and getting them to be installed and do all the logging and evaluation for us. So yeah, huge shout out to the community. And that's all I've got for you guys. So if you have any questions, I think I have a couple of minutes. I don't know if that's part of the schedule, but I'm happy to talk for a little bit longer too. Yeah.
I have a question. So the example that you showed with Nano where it was struggling, right? Have you tried evaluating VLM models? And the question I ask this because so with the Terminal Bench, everything's text-based, right? So it tries to use pkill. But for certain terminal programs, it might make more sense to present using a visual modality. Have you tried evaluating VLMs in that?
So we haven't run that, although many of the agents that we evaluate do have the option to take screenshots and do something with them. So Claude Code, for example, can ingest images, and there's nothing to stop the agent from making a multimodal call to try to understand the environment that it's operating in. So in theory, many of these agents could do this. In practice, they don't seem to like doing that. I think, like, one thing that I want to emphasize about the harness is that we're really not opinionated about how agents should interact with these environments. We used to be. Like, originally the plan was to just do terminals, and we ultimately decided that, like, all the agent makers have their own tools. Some of them are interested in doing multimodal work. And so the way the Terminal Bench and Harbor operate now is you just install the agent directly into the environment, and you let it do whatever it needs to do. So it doesn't have to interact through a terminal shell. Our agents, the one that we've benchmarked, do, but even like Claude Code, for example, it issues some bash commands. It's pretty good at issuing bash commands. It's not the only thing that it does. So yes, your question, since the mics might not have picked it up, was about whether we've tried multimodal models. And we have not personally, although there's like nothing preventing someone from doing very well on Terminal Bench by trying that strategy. Just in practice, it doesn't seem to make that much of a difference.
Thank you for the great sharing. And I think because many people talk about AGI is coming, but when I see your benchmark that those agents just have lower than 50% of the accuracy, I feel a little safe. So do you have any insight that why it do so bad? Or when it didn't achieve the goal, what really happened? For example, sometimes the agent just stuck somewhere, or sometimes the agent hallucinate, or do you have any insight that why those agents fail?
Yeah, totally. So the question was, like, why did these agents fail? Like, why are they at about 50% performance? I think one major problem is there is some overeagerness on the parts of the agents that I mentioned. So for example, they will hallucinate information if they're having trouble figuring out how to use a tool. They'll just say, like, well, the tool isn't working, so I just think that this is probably the answer that I should give, and then it'll get it wrong. When in reality it should probably like persist to try to use the tool or try some other strategy. And so I think that there is like almost an alignment issue here where they get stuck in these ruts and then have a hard time getting back out. And you saw that a little bit with this example of trying to quit out of Nano. Like, it had already tried this same strategy several times, but it just thought that if maybe it kept spamming the keys, eventually it would be able to kill the window that it was in. So I think those are really two common failure modes. One area where they're really good is that they really know how to use the shell. So, like, and you may have seen this if you've tried to use Claude Code, but if you ask an agent to try to find some file, it'll issue some ridiculous find command that maybe you would have never typed yourself or would have thought of, but it'll work, And they're really good at using grep and cat. And I think all of these things are just so well within their training distribution because there's so many great examples of them on the internet that they're able to really execute at using these terminal tools. But yeah, in general, I think they fall into the same problems as other agents. So like poor abilities once their context windows start to get full, difficulty reasoning over durations of more than an hour for probably the same reason. And then I think also, you asked about like kind of a bigger question about like AGI and how far are we away from that. The thing, like, these are all super well specified instructions. There's a degree of autonomy assumed by the agent and that it needs to be able to go and solve the problem itself, but we're telling it exactly what to do. And I think in most real work settings, you're not going to have such well-specified instructions for the agent. And it's going to struggle to actually fulfill exactly what you're trying to get it to do. So I think that's where most of like the gap between agent and model capabilities and real valuable work in much of the economy practically exists. Thanks.
And because you have a spectrum of text, right? So do you will have some feeling
Yeah, like what actually makes tasks hard. One result that we found was that humans are pretty good at predicting what tasks are going to be hard. So we had human annotators go through the tasks and bin them into easy, medium, and hard, and we found that agent and model performance like matched that distribution. And so it's kind of the things that you would expect, like I said, long context reasoning, interacting with the web is something that they struggle with more often than not. But then also like some things that would be kind of hard for a human can be very easy for the agents. So like I said, like generating a regular expression is very hard for a human to do, but the language models can do it pretty perfectly because they just like understand that language well and they know its limitations and all the syntax. So there are some tasks that fall into the other category. Thanks. Well, I think I'm at time now. Appreciate everyone and enjoy the rest of your conference. Thanks.